Now I like putting rocket motors into model aircraft. We call them boost gliders, rocket boosted gliders. But there's a problem that I call the trim toast quandary. Obviously the rocket nozzle has to go right at the back of the aeroplane, because otherwise everything south of the nozzle gets toasted by the 1000° centigrade flame. So that's a toast. Unfortunately, as we know, all model aircraft are finely balanced fore and aft. When the rocket motor propellant gets ejected out of the nozzle, that's all of a sudden a huge amount of mass that's gone out the tail. And this is what happens. It becomes terminally nose heavy and goes into dive, so that's a trim issue. So the only place you can put a solid rocket motor is right at the CFG. Then of course you've got the toast issue. So what do you do about it? Now you can mount the rocket motor inside a tube, like this little cleaner here. Pretend that this tube isn't paper, it's actually metal, or stainless steel or high temperature copper, to take the exhaust gases right to the back of the aeroplane. But we run across what's called the Krushnik effect, a killer back pressure due to excessive buildup of gas in the tube. Something like 80–90% of the thrust of the rocket's just lost. So obviously that's no good. In 1920, a bunch of Scottish schoolboys cracked the problem. They were clearly a smart bunch. Cannily, they ignored every rocketeer's natural instinct to plug the front of the fuselage with a nose cone. So that sidestepped the Krushnik effect decades before Richard Krushnik was born. The fuselage length and rear wingspan are about 4 foot long, fuselage tube diameter is about 5 inches, and it's a canard configuration because they're easier to trim with a rocket motor inside the tube. When this aircraft flew across 3 miles of Loch Lomond, it achieved a speed of 180 miles an hour, which was a record for any size of aircraft at the time. Perfectly trimmed, and it stayed in one piece. The 10-inch long black thing on the bottom left is a rocket motor, with the nozzle on the left. It's 1.5 inches diameter, whereas the tube's just under 5 inches internal diameter. So with the rocket motor round the other way and mounted inside the tube at the vehicle CAG, that left an annular air gap between the tube and the motor, and that's what caused the thrust to be tripled. Why? It's been puzzling me for years. Most rocketeers think that maximum exhaust velocity is king. That's true at orbital velocities, but as Tsiolkovsky knew back in 1903, read your Sutton chapter 2.4, maximum propulsive efficiency occurs when the exhaust comes out of the end of the nozzle at exactly the same speed as the vehicle's moving forward. So the exhaust just seems to hang in the sky, because it's got zero residual kinetic energy with respect to the planet. That's how an aquajet works. Though you fill a third of the bottle with just inert water, the inertia of the water slows the flow of water out the nozzle right down to the speed of the vehicle, giving a hell of a lot more thrust. Intrigued by the continuing performance of the rocket gliders, our Glasgow boys grew up and formed a proper research group in 1936. They realised that the air flowing down their open fuselage tube was mixing with the rocket exhaust. The mixed flow was coming out at roughly the same speed as the vehicle was flying through the air, and not only that, the wasted thermal energy in the rocket exhaust was being used to heat and expand the air in the tube. These young engineers were ahead of their time. Their motors on aircraft quickly get more efficient, and they were using composite construction, fine linen cloth and polyurethane resin, which they imported from Germany. All the research stopped with the outbreak of World War Part II, and they were never heard from again. And yet a mere 8 miles away, at exactly the same time, 1936, the newly formed Paisley Rocketeer Society started working on augmented or ducted rockets. There must have been some sort of cross-fertilization, an article in a Glasgow magazine perhaps. When I joined the PRS, their research confirmed what I discovered later at university, which is that a straight-walled tube most efficiently mixes air from a stoichiometrically burning rocket motor. So here's an augmented tube we made out of stainless steel. Tom turned it down for me, and then I attacked it with ferric chloride to get the wall thickness down 0.5 mil. Having spent hours eroding it, I then cleaned it and wrapped it in insulation. This is superwool, manufactured in Britain. It's a sort of asbestos substitute. I think it's a mineral, but I'm not entirely sure. It's very thin. Well, this one is. It's about 1 millimetre thick. Extremely flexible, very lightweight. And I'm told it will withstand 1200 degrees centigrade. You can drop molten aluminium on it and it just doesn't care. As you can see, I had to use very little to wrap the heat-proof duct. With the superwool wrapped in place with masking tape, it was time to install it in the back of the aircraft, so I got jiggy with a Dremel and a hot glue gun. This compartment right behind the receiver bay is where the little C-class Klima rocket engine is going to go. And behind that is the insulated augmented duct, and behind that is a jig. Alignment of the rocket motor is absolutely essential in rocket vehicles because the thrust is so powerful that the tiniest angular misalignment and all your subsequent flights are just stuffed. It'll never fly straight. With the basic air intake drilled out top and bottom, it was then time to fill in the holes and then replace the cap that I'd hot wired off earlier. The pennies are just to keep it in place while the hot glue dries. Then I removed the jig and she's good to go. See how she flew in my subsequent video. Thanks for watching.